So our first instructors for this session are Peter Boorman and Johannes Buchner. You may have heard Johannes give an invited talk. I think that was almost 2 weeks ago. And on this Bayesian X-ray analysis technique and methods. And Peter Boorman, I believe, is going to give us a presentation about this. So take it away, Peter.
Okay, yeah, thank you very much. So the original idea was to make this as hands-on as possible, right? But I just thought it would help just to bring some things together, just to have a very, very, very brief introduction, just with a few slides, just so we know what's going on. So first off, I just wanted to briefly introduce myself, right? Since everyone has introduced themselves on the chat, I just wanted to show why I use BXA, what I'm particularly interested in. So for those of you who don't know about AGN, here's a sort of simplified schematic of a typical AGN geometry, where we have the supermassive black hole at the center and an accretion disk accreting material and some sort of X-ray source very, very close to the supermassive black hole, very compact. And I'm very interested in the X-ray Compton scattering and absorption that goes on in this distant obscura, sort of 10 to 100 parsecs away, right? And this is the typical spectrum that you get for different line of sight column densities. So this equivalent hydrogen column density that you see, this NH. In particular, I'm very interested in knowing what the average column density is for all AGN. Right. So a simple sort of science question that might sound, it can be quite tricky computationally. Okay. So the first tricky bit is that there are many, many models for torus geometries, okay, for this obscura. And I saw a few people are working on torus obscuration and things like that in AGN, so that's great. But so the different geometric degrees of freedom can be very hard to model and then to quantifiably say if one model is preferred over another. And so that's why I use BXA for this idea of model comparison, but then also the ability to fit spectra, such as in this plot. I'm fitting 3 spectra simultaneously in the same session, much like you would say in XPEC if you were doing data 1.1, data 2.2. But you can do that with BXA. And what's particularly useful is, as Johannes covered very nicely in his talk about 2 weeks ago, you can effectively avoid issues with local minima because you're taking this global view of the parameter space and then condensing down into the parameter regions that you're interested in. This lower panel here on this diagram, this is showing a slightly different approach to residuals. So this is quantile plots, and there is an exercise for that a little bit later on, but very briefly, it's basically showing the cumulative distribution of the data versus the cumulative distribution of the counts. But then all I've done is just subtracted those 2 axes. So a perfect fit on these plots would be a horizontal line. Okay. And then depending on what side of the line you're on, you have either a data excess or a model excess. And based on that, you can then tweak your model accordingly. Okay. If it's too complex or not complex enough. Okay. Okay. And then in the last session, one thing we're going to be covering is this ability of combining individual source posteriors to derive a population distribution from a sample. Okay, so as I said earlier, I'm interested in finding out in a sample of AGM what the column density distribution is, right? But that can be quite difficult if you fit and you have individual posteriors with individual degeneracies, maybe multiple modes. To be able to combine those can be quite a difficult task. And so there are some very cool tools out there that you can use in combination with posteriors that you get from BXA to produce population distribution. And that's what we're going to be discussing in a bit more detail tomorrow. So in terms of the outlines, yeah, if it is needed, I can quickly go over a few quick commands in Sherpa and PyXpec to sort of load data and to fit a model inside a Sherpa or a PyXspec window. The actual commands are covered in the exercises on the URL, which I'll show in a moment. But yeah, if people need more of an introduction to that, I'm happy to do that. But then the bulk of the session is sort of planned to be breakout rooms to work on the exercises. And then me and Johannes can go around if anyone has any questions or any issues, maybe with the installation or the setup or Python versions or anything like that. We can also help with that too. And then, yeah, the last sort of more than 10 minutes, we were probably going to spend discussing any issues, any questions that anybody has in the moment, and then, yeah, that'll be the session. As far as the second session is concerned, I really wanted to reserve sort of the first chunk of the session for any questions that people were able to think about, you know, away from the session in their own time. So yeah, we'll have just a chunk of time just for anyone to ask any questions that they might have, that they might have been able to think of. And then for maybe just a short sort of 15 to 20 minutes, I'll go over a presentation on some slightly more advanced concepts that typically require just a little bit more computation time. There will also be exercises that I'm still working on now, but they will be on the same web link to do this. And they will, the exercises will probably take a little bit longer than an hour session. So we probably won't have enough time to cover all of the exercises. This is also probably true for today's session. But if anyone does have any comments or any queries or anything like that, please do just drop me an email. I'm more than happy to tweak any typos you find, anything like that. Yeah, please do just let me know. Yes, and then the last example that we were going to work through tomorrow was probably going to be the first exercise for the second session on the URL, which is all about creating these population distributions from individual posteriors. Okay, so I kind of rattled through that a bit quickly, but does anyone have any questions on that? Anything at all?
And everyone, if you have a question, if we're not having a lot of questions, then you can go ahead and unmute yourself and ask it. If we're having a lot of questions, we'll start using the raise hand feature to make sure everyone gets asked in order. Looks like no questions, Peter.
Okay. Yeah, if there are no questions, then if anyone doesn't have it, this is the URL with the exercises on. I would say also if at some point I'm doing some coding or anything and it doesn't appear or anything like that, please do just warn me. This is the first time I'm actually working simultaneously on 2 machines during a presentation. So I'll probably be just using the wrong keyboard or something like that. But yeah, please do shout out and tell me. But okay, yeah. So as far as the breakout rooms are concerned, or actually, yeah, would anyone like me to go through briefly sort of Sherpa commands or PyXspec commands, just very sort of basic ones to start with, or they are also included in the session 1 section of the exercises, or would people just like to just plow on and get on with the exercises?
I think we do have a lot of people who expressed interest in doing the Sherpa session, which is not until Wednesday. So that might be helpful to give us a brief overview. Okay, yeah, that's cool. Okay, so I've installed Sherpa with Conda environment. So I'm just going to activate that. And then by running Sherpa, it's got its own IPython. Command there, and then just on the website, if you scroll down or click on the session 1 getting started, so it's got the data to download for this session. So you just click on where it says from here, it should download, and then if you change to that directory so that you have the data files in there, then if you activate Chow and then Sherpa,
And yeah, the first thing is probably a good idea to, well, for this session, we're going to be importing BXA.Sherpa as BXA. By the way, if anyone doesn't want to be using Sherpa but would rather use PyXspec, then yeah, please just go ahead and start the exercises. This is purely for just the Sherpa commands. If you want some PyXspec commands, I can also go over that as well. So to use BXA, you need to use the Poisson statistic instead of chi-squared. So the first thing to do would be to, not that's in PyXspec. So if you do set stat W statistics, so what this is modified C statistics, okay? And there's a link on the useful links part of the exercises for anyone that doesn't know about W statistics, but basically it's where instead of having your own background model, it automatically loads a background model that it's a stepwise function that has a number of parameters that equals the number of bins in the model. Okay, and by doing that, you avoid this the need for having a specific background model, but it does require some sort of minimal binning, which is what I've done on the simulated data that you downloaded for this exercise. Okay. So yeah, hopefully that can work. Yeah. So if we set the statistic there, then also for any plots or analysis that we use, we will probably, just for this session, we'll probably want it in energy instead of channels. So we would do set analysis there. Okay, yeah, so that's mainly the setup that we'll need for the first few exercises. Now, in terms of loading a spectrum, so if we just want to load this one Chandra spectrum, what we would do is load PHA, assign it to ID 1. Ideally, it would be 0, but I'm just doing that to match, I believe, the XSpec notation starts from 1 for spectra, from like 1, 1, 2, 2, etc. And then the name of the file, which is fax1. Yep. And so it shows you that the effective area and the response, as well as the background file, have been loaded in correctly, just because they were in the header of the file. Then if we just ignore the relevant energy regions for this particular spectrum, so for Chandra, it would be 0 to 0.5 in energy space, so in keV, and then 8 keV to the end of the spectrum, so we can just leave that blank. And we need to specify the ID as well to say which one we're ignoring over. Okay, and then in terms of a model, you can just generate a pretty simple model and just call it excess power law. So in Sherpa, when it has XS at the front, it basically means that it's an equivalent of an XSpec model. And a very cool feature you can do is you do dot and then give it a name for your model. So if you do myPow, for instance, I think that's what I did in the example. Yeah. Okay. And then so now you have this model, but you need to actually tell Sherpa that this model is to be assigned to the corresponding data set. So you would do set source or set source model on ID 1, and you would do my mod there. Yes. Okay. I think there's a typo in the instructions. It doesn't have the ID, which I don't know if that would work. Yeah, and then in terms of changing the parameters of your model, so for a power law, the parameters are the photon index and the normalization. So for Sherpa, the main command is set par. So myPow, which is what we called it, dot, so the photon index is the first parameter. Val equals, we could just say 2, which is a pretty good guess for an AGN typically. And then the min we would set here would probably be -3, max would be +3, and we could just go from there. And then similarly for the normalization. And yeah, that's basically for the BXA commands. That's really the only sort of introduction you'll probably need. We just clear that just to make it a bit clearer. Okay, so with PyExpec, it's just a little bit different, but all the commands that we input for the same effect, right? So first, just because we've only initiated an IPython window, so we want to import expec so that we can use PyExpec, right? We also want to import the BXA part, or the expec part of BXA as well. Okay. To change to W statistics, so modified C statistics, in expec, C statistics where you don't have a background model are automatically W statistics. Okay, so what we would do is fit dot stat method equals cstat, I think. Yeah. Then changing the from channels to energy is just for plots, I think. So you would do, for instance, this sort of thing. But there are also, you can change to different units if you prefer. Now for PyExpec, if you want to use a plotting device like you would in regular expec in terminal, you just do plot.device equals instead of CPD that you might be familiar with in terminal. And so the same commands work, but it has to be a string. So you would do /xw if that's what you're used to, or I think other ones like /xs maybe. And that'll bring up a window. You won't have been able to see the window that came up because I'm only showing terminal, but it did come up. Then that's, yes, so in terms of the setup, that's the main sort of setup that we do. Then for loading individual spectra, you can do S equals spectrum. This one. That's how you would load a spectrum into the first data set. Then in terms of ignore, it's just a slightly different command to Sherpa. So it's just S, so for the spectrum dot ignore. It keeps going. There we go. And it's the same syntax that you would use in the terminal. Okay, yeah. Then in terms of a model, again, it's just slightly different. So it's just my mod equals, and the main thing is the capital M model. And then in brackets, this time, if we just wanted the power law, we would just do power law, and it prints out to show you that that's what you've got. And then there are various different ways to change the parameters. One way is to do the name of your model. So it was my mod dot power law dot, in this case, index values equals, and the order of this kind of matters. So the first number is the value. The next number is the delta used in a local fit. So this number doesn't matter for BXA. This would be used for the Liebenberg-Markov algorithm, I believe. And then the minimum. So here that would be -3. The next number is the sort of soft minimum. So it's often called the bottom in expec, the bottom parameter. But here we're just going to set it to the same value as the hard minimum. And then the soft maximum, or the top value, we're going to set to the hard maximum as well, which is 3,3. Okay. Again, like if you are new to this, don't worry. This is all included on the breakdown at the start of the exercises. So that's set the photon index, and that's all I think you need to know before the first exercise. Okay, so on the web page, so if we do exercise 1.1, so this is all about prior predictive checks. Okay, so the thing that's powerful about BXA is that you can fit from a predefined global parameter space. Okay, but you have to, or it's good practice to check that the prior parameter space that you defined makes sense for the data that you have, right? So for instance, for this data, it's a relatively faint in terms of the intrinsic source flux. So if we were to set the power law normalization to a prior between 10,000 and 100,000, then that would be a bit silly, right? Because on the y-axis, if you plot the data, it's clear that the normalization should be a lot lower than that, right? So it probably doesn't make, you know, a lot of sense to do that here, but it's just an example. And for more complex models, it is very useful to effectively plot the spectrum that you get for just a selection of values from the prior, just to see if the priors make sense. Okay, so just because I have PyXspec open and every time I change terminal tab, I have to reshare my screen, I will do this one from PyXspec. I hope that's okay. I have included the PyXspec and Sherpa commands for everything on the exercises. So if you would rather have Sherpa, then yeah, please do just look at those. So for here, so the first thing we're going to want to do is we've set reasonable parameter ranges for the photon index, right? So the next thing we want to do is we're going to set reasonable parameter ranges for the normalization, right? So the one remaining parameter that we've got. So what we would do is we would say mymod.powerlaw.norm.values equals. So a first guess that we can do from the plot of the data. Oh yes, just so you know, I sort of skipped past it just because you can't see my plotting window, but plot commands in XSpec or in PyXspec, if you want just regular ones that you would get in equivalent of just XSpec, then the command is just capital P plot like this, and then the equivalent command that you would do in XSpec. So for instance, this time we would do plot L data, and you should get a window up, right, where the spectrum is sort of on a level of, say, I don't know, 0.01 on the plot. Okay, so that kind of tells you that the normalization should be, you know, within that sort of range. So what we can do is we can do mymod.powerlaw.norm.values equals, so 1, let's just say 1e minus 3 for the value. So this is just the initial value of the parameter. And this doesn't actually matter for BXA, because as we said, it doesn't start in one position in the parameter space. It starts in a range defined by your prior, right? So the key things that we're going to want to change are not this number either. So that's just the delta. I'm just putting that in just in case it throws up a warning or an error. But the main numbers are, so this number, right? So the first is the hard minimum. So that's going to be, going to set that to arbitrarily very low value relative to our spectrum. So let's just say 1e minus 8. Then the soft minimum, which we're going to set to the same value just for now, but that doesn't really matter because, like I said, for BXA, it only needs the hard minimum and hard maximum. And then we're going to set the max to 1 and 1. Okay, so do that. Okay, so that's defined your parameter ranges, but now the next step in BXA is that you're going to want to define your priors. Okay, so the prior transformations that in PyXspec you feed in prior transformations. In Sherpa with BXA you feed in the priors or a global prior function that you create from your individual priors, as well as a list of your parameter values, okay, or your parameters even. So here we're going to just define transformations equals, and we're going to define a list. So the first thing we're going to do is we're going to create a uniform, prior for the first component. So the first value that goes into this is the model, so that's my mod, and then the parameter itself. Okay, so that's going to be mymod.powerlaw.index. Okay, So that's the first value in the list. Then the reason we've here, yeah, so actually, yeah, I should explain. In the online exercises, I have said that you can assume that the power law photon index is a Gaussian, right? So alternatively, if you didn't want to use just a uniform prior, so just a non-informative prior, you could also, you can also just change that to Gaussian there. And the only difference is that you would also put that there. But then the next value is going to be the mean of this Gaussian, right? So I think mine I said 1.9, I can't quite remember, but it probably doesn't matter right now. And then a spread of say 0.15. Okay, and that will create a Gaussian prior. Then for the normalization, because the normalization, we designed it to spread from 1e minus 8 up to 1, it covers a lot of orders of magnitude, then the appropriate prior there, if you don't want to have an informative prior, is just to have a non-informative prior, but over log space. Okay, so a log uniform prior. So what we would do then is BXA.create log uniform prior for, oops. And then the second parameter. So that's going to be first the model, then the parameter. Yeah, it keeps disappearing. I don't know why. Okay. That, I think.
Yeah, that's funny. I see the focus disappear.
Yeah, I don't know why. Okay. So yeah, and then if you've done it correctly, then BXA will print out the priors that have been created from that. Okay. So that's, yeah, that's the priors. Then the next step is you have to create what's called a solver, so a BXA solver. Okay. So basically this holds information about the fit that can then be used afterwards. And it's sort of defines the input parameters for your fit. So if we were to just do solver equals BXA.BXA, oops, solver, I think it's like that. Yeah, so capital BXAS and then solver. And then all we're going to do is just say transformations equals transformations. And then also important that we set an output file's base name. So this basically, BXA is going to create a folder with all the fit information, all the plots, the points that are generated, the chain file, and things like that. And it's all going to put it in a folder that's called this name. Okay. So here we're just going to say my mod, I expect try not to make it too long, just in case the maximum length is exceeded. But that should hopefully create the solver. And then after you've created that, all you have to do, well, actually before we actually run the fit, the next thing we're going to do is we're going to check that they make sense. Okay. So I had a bit of trouble getting the solver.set parameters to work, I think, when I was trying. Yeah. So instead, what you can do is on the web page, I've created a link to the set parameters part. So on exercise 1.1, where it says perform prior predictive checks. If you go to number 2, where the text is blue, if you click on that, it will take you to the equivalent code. If you just copy that into your script, I have it here for me, and it should look something like this. In the meantime, I'll just copy that in there. And so what we're going to do is we're going to, just for 10 random samples of the prior function. We're going to plot what the spectrum looks like for that equivalent prior points. Okay, so if we just do for I in range 10, this is probably quite a primitive way of doing it. But what you can do is you do values equals solver.prior function. And then, oh, by the way, we would have to also, I should probably do that for me as well. Have to import numpy. So yeah, we're just going to sample 2 random points from the photon index and the normalization separately. So inside here, we're going to do size equals the len of solver.param names, because there's 2 parameters. That should like that. And then we're going to set the parameters of the model to transformation. Oops. We're going to basically set the parameters to those values that we've just sampled. And then for PyXspec, we want to just plot the log data. So you can do LD or log data. And then because we're doing this in a loop and we just want to manually check just to see if everything's reasonable, quite primitive, but you can just do pause input like that. And then essentially, again, you won't be able to see, but it's brought up a window with the spectrum. And so each time you go through, it will show a spectrum that's sort of above and below the points if you go through enough of them. Okay. And all you want to see is basically that wherever the spectrum lies, if it's above and below or in roughly in between the data points, then it's a good prior to use, which we know for this case because we can pretty much guess what the normalization is going to be. But for more complex models, that's why this can be useful. Okay, so we've done the prior predictive checks. Are there any questions on that specifically? Thank you, Johannes, for putting, yeah, so if you want to use set parameters, you can use the codes that Johannes has put in the chat to do that instead of copying it from the source code.
What is being displayed in your plot window? Anything?
So yeah, it's basically showing the spectrum and then the data, sorry, and then the model spectrum. Would it help if I
maybe
shared the plot window?
Yeah.
Yeah. Okay. Let me just stop sharing. So I'm curious if this is actually going to update itself when I do this.
We'll find out. Yeah, I see it updating.
Okay, yeah. So as you go through the loop, you can see that the prior goes above and below the points, right? Like you would want for a reasonable prior. A bad prior would basically be, in this particular case, if all of the spectra were above, say, 10, right? Then you'd know that something's gone wrong or the wrong range has been chosen.
So that loop is just showing you where your priors are or the bounds of the prior are, and that's the checking the priors part, and then the next part would be the actual. Exactly
right. Yeah. So this is just showing that this is effectively, I guess the equivalent would be in if you're doing a local fit to plot your spectrum beforehand, just to see if you were close to the data points, just so that it doesn't get lost in the local minimum when you click fit, right? So in this case, yeah, you're just checking that the range you've chosen is above and below the actual data.
And in this case, it's the overall data, because that emission line, that iron emission line is way above that that prior limit, but that's fine.
Yeah, no, yeah, that's a very good point. And so that's why a little bit later, the ion emission line, it basically shows that you have to change the model, right, instead of changing the priors.
Okay.
Yeah. But yeah, so that's a very good point. Yeah. Okay, so if I stop sharing. So now that we've checked that the priors are right, so next is so exercise 1.2, and so in normal PyXspec or normal Sherpa, we would just do fit, right, or fit.perform in PyXspec. But here, all we have to do is just say results equals solver.run, resume equals true. Now, I should warn you that by doing resume equals true, you're basically saying that if there's already a partly started job or a completely finished job with the same output file's base name, BXA will try to open that one and sort of restart the likelihood that it's got on that fit. Okay, so if the model's changed slightly, or if it's just completely the different model, but you just kept accidentally the output file's base name, just be warned that will be why you get an error message. Okay. Okay, so after we run that, you should get a printout that looks kind of like this. And what this is showing on each iteration, it's showing the range that BXA is finding in the different parameters to be the correct one. Okay. So you'll notice as well that by setting a log uniform prior on the normalization, BXA has effectively created this slightly new parameter, which is log norm, and varied it in log space. In Sherpa, you would have to create the log normalization yourself as a new parameter, and then input that into BXA. And the instructions to do that are on the web page. Okay, so yeah, it tells you when it's effectively approaching 100% for finished here, and this is the evidence. And then when it's done, it will print out the log Z. So this is the Bayesian evidence, and it will print out the best fit parameter values. Okay. So for anyone that's interested in pandas or anything like that, I find it quite useful if you were to want to use the chain values. For instance, if for the error propagation exercise in exercise 1.4, or if you wanted to produce your own plots of Quantile plots, or to work out your own quantiles, medians of the parameters, or maximum posteriors of the parameter values, then what you would have to do here is just to say, just to set up an empty data frame, fill it with, so the data is going to be the results and the samples key. And then the columns of your data frame are just going to be the param names that we used from earlier, right? So the solver.param names. Okay, and now what that does is you can do dataframe.head, and as you can see, it's basically got the flow index and the log normalization values as a data frame that you can then use. Okay. Okay, so in terms of, what is the time? So yeah, we are slightly running out of time. Yes, okay, so Johannes is probably the best person to ask about the ins and outs of the different quantities here. But very briefly, from what I know, so the likelihood range being considered on each iteration is shown in this part, I think, and then the number of iterations over the number of evaluations is shown here, and then the efficiency is effectively showing how many points have remained from the original starting point. Okay, so nested sampling basically, well, briefly works from throwing out points that have the the worst likelihood and then refilling in the region in your parameter space that have better ones. And so if you have a very, very big parameter space, then as it removes points, you're going to lose points. And so this basically shows you how many of the points have been removed. Okay. So in terms of the model comparison, right, because we're slightly running out of time, there are a few interesting things that you can do. If I just try and up here. So the first one is the AIC, so the key information criterion, which I have somewhere. So yeah, there are two basically model comparison techniques that I was going to cover in this session. So the first one is the AIC, which is basically a method that penalizes extra model complexity when it's not warranted from a particular data set, right? And then there's the Bayesian evidence, which is kind of it's the marginal likelihood, right? So it's an equivalent of likelihood ratios, but where you factor in the priors that you've used as well. Okay. So if I just yes, so I've run the model fits for a power law model, a power law plus Gaussian, an absorbed power law, and then an absorbed power law plus Gaussian. Okay, so 3 different models. Okay, and I'm hoping this will work if I type these in. But basically, all this does here. So we're using the JSON model here to load the results, which are stored in your output files base name /results /info /results.json. Okay, and that will show you the log likelihood and the degrees of freedom, and then the AIC is just the 2 times the degrees of freedom minus 2 times the log likelihood. Okay, so after doing that, if you then type AIC, this basically shows you that the smallest AIC is for the line of sight model, absorption model with Gaussian line, which, as we said earlier, the line is very present, right? So yeah, that's basically showing that the most favored model with the AIC, because it's the lowest, significantly lowest as well, much more than, the difference is much more than 2, is this model here. Okay, so another way to check if a model is preferred is to use model comparison. And one nifty thing on the BXA website is the model compare script, which I've linked to in the exercises. So exit there, and I'm hoping this will work. So if you type Python 3, then the name of the script, which you copy to the directory that you're in, and then the 3 output file base names that you've chosen for your 3 models. Okay, and then I'm hoping that will work. Yes, okay. And what it does is for every single model, it orders them by the difference in their log Bayesian evidence. Okay, and although the exact threshold for all of these model comparison techniques, really strictly speaking, should be determined with simulations, one general rule of thumb that you can use is the Jeffrey scale, which effectively says that more than a value of 100 is very, very likely that a model is favored, okay, for good data quality. And so in log space, that would be a factor of 2. And because the difference between the line of sight absorption model and the line of sight with an emission line model is 13.1, so much higher than 2, here it tells you that the fit is good. So yeah, that's a way of selecting a favored model. So in terms of this idea of the exact threshold for AIC and also log Z, to figure out which model is preferred, yeah, the exact threshold, you should really, or well, it's good practice to calculate that with some simulations. And I will be covering that briefly in my talk tomorrow, and also for the exercises. I think it's exercise 2.2, which is yet to be up on the website, but it will be. So I know I did go through that quite quickly. Sorry about that. But if there are any questions on any of that, I'd be very happy to take any that you might have.
I think I want to see the fit. If you don't mind sharing your fit.
So yeah, this will be the fit for the first model. So just a parallel. Oh, I've just loaded the Sherpa one, which is always good. So if we do, yeah. Okay. Right. Yeah. And then because we're doing resume equals true, it will be a very quick process because the points are already there, so it just goes through them. And then can't remember if in the expect version it automatically sets it to the best fit. Yes, it does. Okay. And that's the best fit you get.
So this would be a case where when you do a model comparison, you'd show that another model would be improved because you'd fit more of the features.
Yes, yeah, indeed. There is also some ways to do model verification as well. So instead of trying to find a better and better model, you can also check if the model that you have currently is a good fit. And that was also something I was going to go over tomorrow, but briefly, it's basically what we did with the priors, but we're sampling, instead of from the prior distribution, we're going to be sampling from the posteriors and comparing the W statistic from simulated data to the actual data itself. So they're posterior predictive checks. And they effectively show if the fit on average for the data quality that you have is a reasonable fit. So yeah, this basically shows that there's a nice sort of dependency between the parameters, between photon index and normalization, which kind of makes sense, right? Because if you change the steepness, then the normalization will also have to change correspondingly. So you can't know both perfectly simultaneously, is what that's showing. Mm-hmm. But what's powerful about this is if you have a slightly more complex model where parameters might be degenerate with one another in particular ways, or if there are multiple modes, then this method should be able to show those. And then that's why in the error propagation exercise, so I think it's 1.4 maybe.
Right.
If you use the actual chain values from this, then all of those degeneracies and multiple modes, they're all conserved. So when you create uncertainties on parameters that you've derived from the other parameters, right? So in that particular example, it's the equivalent width. Then those uncertainties are preserved, or the structure of those uncertainties are preserved, which is quite powerful.
And those files are in the directory that it put all of the best fit and all the files that when you set the output directory, they're all located in there.
Yeah, yeah.
Okay.
3 plots that are automatically put in there. In the expect module, there's also additional code, which I've included on the exercises, where you can plot the posterior convolved and unconvolved models as well, just to see the range in your models. And then you can also do that for the model components by freezing different components to 0. And then you can basically plot out your individual components. So one of the main ones is the trace plot. So that basically shows the progress of the fit over the duration. So the minus log x on the x-axis in the trace.pdf basically shows where you started from to where it finished. And then the final one-dimensional posterior distribution. And then the run, again, it shows the progress, but the progress in the evidence, yeah, in the different values, and it basically shows that as the duration goes on, eventually the normalized likelihood that's being numerically solved by BXA by the nested sampling is approaching 1. So that's the second panel from the top. So it's just, yeah, they're just different ways of showing the progress of the fit, just to check that everything went all right during the fit.
Peter, what is it? Could you ls the directory that it created and just show us the list of
sorry,
files?
I keep forgetting that. Sorry, you can't see. So it's going to be. Yeah.
So,
So
that's okay. Quite a bit. Okay.
Yeah. So if anyone's ever used MCMC chains in XSpec, BXA outputs an equivalent file called chain.fits. So you would just do chain load file name in XSpec, for instance. Then, yeah, the chains, the debug.log basically tells you how the fit went on. It's quite useful for seeing how long it took, for instance, if you should change any input parameters to make it run a bit faster, anything like that. Let me see. Just jog my memory. Yeah, so extra probably won't have anything in it unless you do extra stuff on it. Info, so that's going to contain your results.json and then also your posterior summary that's output in a CSV file. The plots, again, so the corner, the run plot, and also the trace plot that we just went through. And then results is going to contain the points, which I believe is what's read in when you do solver.run resume equals true. That's the file that it uses to restart the run. Okay, yeah, so this is just a quick talk for the second session, just to put everyone on sort of a level footing, hopefully. Oh, that's the wrong keyboard again. Okay. Yep, so this session, what I was broadly going to go over was the main thing is posterior combination. So this idea that if you have a sample of sources and then you fit each source with a particular model and derive a posterior on some parameter, the basically methods or optimum methods to combine those individual posteriors into a sample or a parent population distribution. Okay. Then we are going to talk a little bit about model selection and the model selection thresholds. So yesterday I mentioned that in terms of Bayes factors, it's generally, generally sometimes you can assume that a value of a Bayes factor more than say 100 is very, very strong to favor one model over another, but the exact number itself does depend quite significantly on various different things, such as the data quality that you're actually fitting, right? And it kind of makes sense if the data isn't very good, then your model selection thresholds or your model selection techniques should not really make a decision on a model, or it makes more sense to not make a decision on a model if the data quality isn't good enough to warrant it, right? So there are some methods where you can calibrate those thresholds, and for particular observations that you might have, you can run a whole bunch of simulations and different methods to try and detect or try and figure out what the false positive rate is. So how many times a particular threshold will select the correct model over the wrong one. So then the third thing was more about model verification. So it's all well and good having nice ways to select models, but if you select one model as being the best out of a group of models, how can you then say that that model you've selected is actually a good fit? And so it's a bit more about goodness of fit. And there is one method that you can do, again with simulations, but called posterior predictive checks. Now, I was considering talking a bit more about binning and background modeling. We probably won't have time, just because there's a whole bunch of other stuff I was hoping to go through. in terms of the exercises, but I have written quite a bit on the exercises, and then there's also a very, very cool, I think it's a GitHub page, but written by Giacomo Vianello, who basically talks through the issues with CSTAT and also the benefits of it, and how to correctly bin your data to fit particular models. And then in terms of the auto background, exercise 1.7 runs through how to simultaneously fit a background spectrum and a source spectrum in Sherpa using BXA. Okay. So just to go back to the same example that I mentioned yesterday, just because it's the one I'm most familiar with, so sorry if people don't like that. So in terms of Agm obscuration, the problem that I mentioned is that the idea is that you have this X-ray source very close to the supermassive black hole, emitting some sort of power law emission, or some sort of emission that can be approximated with a power law. It's passing through some obscuration, and then as it does that, the X-ray photons are scattered and absorbed, and depending on how much scattering and absorption you get or that you can detect in your spectrum, which I'm showing here on the left with this inset, you can predict what the line of sight column density is. Okay. Now, of course, there's lots of degeneracies here to do with the geometries that we're playing with, because for different X-ray models, you can assume a lot of different complex geometries, and there are a lot available publicly at the moment. Yeah, there's the number of geometric degrees of freedom is very high, right? So that's why you would want to use things like BXA and more sophisticated fitting methods, just to be able to explore the local minima. So this is effectively the solution, but also the problem, right? So for all of those geometries, and then for also some other different forms of models that are assuming different things, you basically have a different model. Okay, so here I'm showing a large number of models for a particular project that I was working on, where for a group of sources, I fit this number of models to every source. Okay, now the issue associated with this is that once you fit all of these models, which in their own way has some sort of line of sight column density, the issue is that if you were to assume just one model, then you would have that number of column density distributions, right? Which is, of course, not useful, okay? And as you can see, for the models up here, the column density distribution you get basically finds that you have the majority of them are unobscured, right? With column densities around 10 to the 20, whereas more physically motivated models seem to find slightly higher fractions of heavily obscured sources, okay? So the thing you really want to be able to do is to be able to select the correct model, as we've been saying with model selection. And yeah, once you have done that, once you have a model per source, then it's also a matter of combining the individual posteriors. Okay. So in terms of posterior combination, one very nice way of doing it is with Bayesian hierarchical modeling, where you simultaneously fit for the parameters of the individual distributions simultaneously to the parameters of the global population distribution. And here on the right, I'm showing one way one can do this, which is supported by Posterior Stacker, which is a slightly different method of doing this sort of fitting, which I'll get onto in a sec. But the idea is that for every bin in your histogram or in your distribution that you're trying to fit in your parent population, every single bin is a free parameter, okay? And the free parameters of that population is then informed from the individual line of sight posteriors from a single or from the individual observed X-ray spectrum. Now, what Posterior Stacker does is it essentially takes the integral involved with this problem and simplifies it numerically. Okay, meaning that it's a lot quicker to be able to calculate the estimated population distribution from an arbitrary number of individual posteriors that you feed into it. Okay, and this is covered very nicely in Baroncelli et al. 2020. So I do recommend anyone interested in more of the finer details really taking a look at that. Okay. And so for anyone interested, that's what you end up with here when you select models in different ways. So I'm showing here on the left, this is when you select models based on the Bayes factors versus when you select models with AIC, and the answer, thankfully, is that they are consistent within errors, right, with these models. Now this is a function of your data quality, as we've been saying, but it is also a function of the limitations of your models, okay? So that's why, for instance, this big drop here, this isn't a physical thing. This isn't something that the individual source column densities are actually doing. It's just because the models, or the vast majority of the models that were selected by these methods, tend to disfavor, or sometimes don't even go above 10 to the 25. Okay, so it's always important to know the limitations of your models for your individual posteriors and the assumptions that went into them before getting any conclusions out of the parent population as well. Okay, so now that we've spoken a bit about that, and hopefully there'll be time for me to go through the first exercise of session 2, which is on the website. But talking a little bit more about Bayes factors or model selection in general. And again, this is a figure taken from Baroncelli et al. In 2020, essentially showing the difference in Bayesian, so effectively the Bayes factor as a function of signal to noise, right? So if you, can you see my cursor? Yeah. So if you see the x-axis is actually decreasing in signal to noise, and the difference in Bayesian evidence, right? So the Bayes factor between two particular models, right? The difference is much greater until you reach a signal to noise of around 7 for this particular work, where the difference levels off. Now, I should say that this particular figure from the paper is actually based on a whole bunch of simulations that they did, but the actual observations, they found similar results to the shape of this plot as well. Okay, yeah. So this is where this idea of simulation-based calibration comes in for model selection thresholds. Okay, so the idea is that you simulate many models for a particular brightness. So here I'm showing a very nice, or a plot from a very nice set of simulations from Johannes's 2014 paper, where you assume different levels of brightness of a particular source, and you simulate a bunch of models and then fit with various different models and check how many times for a given, in this case, Bayes factor threshold, the correct model is selected or the wrong model is selected. And these plots basically show that as you get to a value of as low as actually 10, in contrast to the value of 100 I was saying earlier, for these particular simulations, the correct model was tending to be selected. So this is actually, I think, exercise 2.2. Now, the reason we probably won't do this in the session today is it does involve simulating maybe 100 or so spectra and then doing, for our example, at least 3 fits per spectrum. So it'll be around 300 BXA fits, which would be probably a bit too long to do in an hour session. But yeah, I do recommend anyone interested in this to really give it a go, because yeah. Okay, so as I was saying earlier, right, so, okay, you can have a whole bunch of models, and this is a plot that I made for a particular source that I was fitting with NewStar data. So for those who don't know, there's 2 cameras on NewStar, so FPMA and FPMB. And then I was simultaneously fitting the new star spectra with a soft X-ray spectrum from Suzaku, so XIS3. Okay, and so here I've split them into their individuals and then also added up the individual values as well. Now the only values that change in the individual panels is the x-axis, because the Bayesian evidence is the same for the global fit. And as you can see, you can say that there's a given threshold, which is the best model minus, in this case, I think it was a factor of 100. So in these units, it's going to be log z over z p1, difference of 2, right? So log of 100, which is the width of these lines, okay? And all of the colored in stars are the models that are sort of selected as being, you know, within that threshold, okay? But this is all well and good, right? You can select a number of models, quite a few models in this case, that are actually consistent with being the best model, right? Or the most favored model even. But how do you actually check that model fit is in fact good, right? So this is where model verification comes in. So we spoke very briefly about QQ plots yesterday, but just to go over them in a bit more detail, they're essentially an alternative to residual plots, where instead of showing the binned residuals, you plot the cumulative distribution of the observed counts on the x-axis, and then the cumulative distribution of the model counts on the y-axis. Okay, and now the benefits of that is that you don't have to bin anything, so it's completely unbinned, so you can really pick out the finer points where your model might be missing something. And marked on for this particular plot from Johannes' 2014 paper again, is the different energy bands where particular effects start to come in for the different models that are shown with the 3 colored lines. So for instance, where there's a data excess, the line deviates into this direction, right? So here, there may be a line that's not being fit, for instance. And then also at around AKV or beyond, there may be a line that's not being fit so well, say in the pink model versus the yellow one, for instance. Then just to briefly flag it up again, I think I showed this plot yesterday, but there's another way of doing it where you essentially show the y-axis minus the x-axis, right? Which is what I'm showing in these panels down here. It's basically the same plot. The only reason I've got a shaded region is just because I've plotted the posterior 68% range in the values as a shaded region, just showing that with this model, it is actually broadly consistent with just being a horizontal line, so being a good fit. Okay, so that's sort of a qualitative way of saying that it's a reasonable fit. But what if you want to make something a bit more quantitative? Then this is where posterior predictive checks comes in. Okay, so the idea is that you fit your model with BXA, then you sample like a few posterior rows, or if you want to keep the runtime down a bit, you can sample just the best posterior row, so the best likelihood row. Then for that particular row, you're going to have a whole bunch of parameters for your model. So you load those model parameters, and then from that fit that you've now loaded into XPEC or Sherpa, you would simulate a whole bunch of spectra, and then on every time you simulate, you would remember or note down the W statistic or the C statistic, depending on what statistic you're using. And then after the simulations, you would then compare that to the original statistic of your original real sampled posterior row. And you end up with diagrams like this, right? So for what I was showing earlier, where I had that new star plus Suzaku fit, the blue distribution in the background is the simulated one. And if the model that I'm using is able to explain all the individual nuances in the data and all the individual dips and things in the data, then they should agree very nicely, which they do here, right, for XIS3 and FPMA. The difference in FPMB is being caused by just being a lower signal to noise for the FPMB spectrum than FPMA. But yeah, overall, if you add them all together, you end up with an acceptable fit, right? Because it's reasonably inside the simulated distribution range. Okay, so that was probably quite quick for these extra concepts, but just briefly, so we've covered Bayesian hierarchical modeling, basically this idea of combining individual posteriors into a sample distribution. Then there's also ways to work out the correct sort of model thresholds or model comparison thresholds to use for any particular data set quality that you might be using. And then there's also posterior predictive checks to get more of a quantitative measure of the goodness of fit for a particular fit that you get with BXA. Yeah, Johannes?
Yeah, just wanted to say a couple more words, if I may. Can you go back a couple of slides?
Yeah.
To where you talked about the sample distributions, about the hierarchical model.
Yeah. This one?
Yeah, so this you can, even if you just have one model that you fit and one particular parameter that you're interested in, you can apply this to get a distribution of how this parameter is distributed in your sample. Here we're not doing any correction for selection bias, so it's really just the distribution of the sample, not of the unbiased underlying population, unless you have a complete and unbiased sample, of course, then it would be the same. Here is shown this kind of binned model that Peter was demonstrating, but you can also use a Gaussian sample distribution, and then you estimate the mean of that distribution and the width of that distribution over that parameter of interest. And then I wanted to say something about the model fit that you showed. You showed some spectra and the posteriors on those.
This one?
Yeah, here. So you have very nice data actually. So your uncertainties on your posterior on the model are actually very small, but you could imagine different situations where they would be much larger. And one way of doing posterior predictive checks is to generate counts from each instance of your model. And then you would have counts at each energy channel, right? And then you could look, do your actual counts that you observed lie within that distribution of counts? And that's one common way to do posterior predictive checks. What Peter later showed is to look at a derived quantity, the W stat, which sort of squashes all of that information together, sort of a summary statistic, and look how that is distributed.
So yeah, if you scroll down on the exercises, so yeah, just a brief introduction. So for session 2 in general, I've tried to include 2 code snippets that basically you can use to sort of as a basis to just simulate a model from Sherpa or PyXspec. Please do let me know if there are any typos or if it just doesn't work. But it worked on my machine, so hopefully it'll be okay. But yeah, they will probably be more useful for questions or exercise 2.2 and 2.3. But for the Bayesian hierarchical modeling, so for, actually I'll make that a little bit bigger, that helps. Right, so in the interest of time, yesterday I generated a whole bunch of photon index values from, I think, a Gaussian distribution. Yeah, a Gaussian distribution of 1.8 plus or minus 0.5. Just a warning, I did realize after I did that that was very wide, considering I've only actually done 30 sources. So yeah, just do bear that in mind. But you can download a zip folder from the link here, which will basically have all 30 Ultranest or BXA folders, the output folders that you get from the fits. which is what we will use for this exercise. So if I change, actually, first just make sure I'm in the right environment. Then I'm just going to change to the where am I? Right directory. Yep. Okay, so yeah, I have all of these folders in here. Probably a bit easier if I just do. Yeah, so this directory here. So the ones that say fitsim, these are what you will download when you click on the link, and they basically just contain everything from a PyXspec output. Okay, so for this exercise, you won't need PyXspec or Sherpa. I see Tron. So yeah, don't worry about that. But the first thing you'll just need to do is do pip install Posterior Stacker. If you don't want to do that, you can also just download the scripts themselves from the GitHub page. Now, the first thing we want to do for Posterior Stacker. So as I mentioned, it's kind of a numerical approximation of this integral, or this, I think it's a double integral involved with Bayesian hierarchical modeling, right? So as this numerical approximation, what it does is it takes a certain sample of the posterior rows from each fit, okay? And so there's a very nice script included, which is the load ultranest outputs script, and you have to give it the name of all of the output directories, and then specify how many samples, how many rows you want to take from each one, and the parameter that you want to take from that distribution from the posterior, and then it'll output it into a particular file. Okay, so if we just let me check that I've actually got the right environment, which would help. Oops. No, I have not. Okay, so yep. So what we're going to do is that. So you're going to type load ultranest outputs.py. If you haven't installed it with pip, you just do Python 3 load ultranest outputs.py, and then immediately afterwards just list with a separated by a space all of the directories. Okay. Then the next argument is going to be samples, so the number of samples, and here we're going to sample 1,000 from each one. Okay, so 1,000 rows of every posterior for each source. Then we're going to tell it which parameter we want to take out of the posterior. Okay, so we're interested in the photon index, and for these particular runs, I called the parameter pho index because we were using PyXspec, which uses a case-sensitive version of the parameters. And then the last thing we're going to say as out, we're going to do we're just going to call it posterior samples. I'm going to call it 2.txt, but you won't have to. It's just because I've already got one I was testing earlier, which I will keep just in case this does go wrong. Okay. So then it'll tell you the columns of the posterior, and if you were to list, yeah, you should then have posterior samples too, .txt or whatever you've called it in your directory. Okay.
Do you want to show us what's in there?
Yes, I was. So I was going to go. So on this part, this is where I load it into pandas. But basically, if you import numpy, this file can then be loaded. And this is essentially what it is. So it's got 30 arrays of length, 1,000 inside an array. So it's a two-dimensional array. So if you do, so yeah, it's just got for all 30 folders, the 1,000 posterior rows that's been sampled. So then on the web page, so you can follow this code just to print out basically an approximation of all the data points, which will end up looking like this. So what this is on the y-axis is just an arbitrary number for the data point number, okay? And on the x-axis is the photon index value indicated by the 50th percentile, and then the lower point of the error bar is the 16th percentile, and then the 84th percentile, okay, is the upper one. This is just a way to sort of visualize the data. This doesn't show the shape of the posterior, it's just sort of an approximation. And as you can see, actually there's not a whole lot of asymmetry with this statistic, with this method of using quantiles. But that doesn't actually say anything about the posterior. But this is just for a visual aid. The actual posteriors themselves are still stored in posterior samples.txt, which is what's then going to be fed into Posterior Stacker. Okay. In terms of the next bit is just to then run Posterior Stacker, which is then going to combine these into this parent population, approximating, as Johannes said, with the Gaussian model as well as the histogram model. Okay. So earlier, when I mentioned the issue associated with simulating from such a broad distribution, but only having 30 sources, is you can kind of see it here. So the distribution I simulated the photon index from was 1.8 plus or minus 0.5, which, as you can see, in terms of the data points, it's pretty much there. But in terms of the points that are going to carry the most statistical weight, so the ones with the smallest errors, so the ones with the smallest errors, these are going to be the ones that drag the distribution towards the left here. So spoiler alert, it will probably come out with a number that's slightly less than 1.8 plus or minus 0.5, but it will be consistent with that number. Yes, Aneta, did you put your hand up? Or?
Yes, I have a question about this errors or posterior. So in your plot, in your figure, it looks like all the uncertainties are symmetric. So do you require the symmetric errors?
No, not at all. No. So this it kind of turned out like that. I think that's because the simulated models are just basically an absorbed power law. So it's quite a simple model. And so the actual distributions of parameters that I was probably getting out were probably fairly symmetric, but there's no reason to have such a symmetric effect. Are there any other questions? I think, oh yeah, it was answered in the chat, I think. Okay. So then the last thing is to run Posterior Stacker. So what we do is we write posteriorstacker.py, then give it the name of the text file, or the output from the previous commands. Then what we're going to do is we're going to give the lower limit of the model that we're going to use. So for the histogram model or the Gaussian model. So from the plot that we made up here, it kind of makes sense to make it between 0.5 and 3, right? So we'll put 0.5, then the upper limit, so 0.0, and then the number of bins in the histogram model. Okay, so we can put 10, for instance, here. And then the name that we'd want on the x-axis of the plots that Posterior Stacker produces. So if we just say index. Okay, and hopefully that should all.
You wanted to run in the shell.
Oh, sorry, yeah, of course I did. Yeah. Thank you. Yeah. Then hopefully that one should work. Ah, yes, but because I'm using the wrong Conda environment, this won't work. So what I can do, hopefully I have it in here, yeah. So I'll just activate the other one. Sorry about this. Hopefully that will work. Yeah, and it'll come up with the Ultranest fit first for the, I think first is the histogram model. Yeah, I think so. But yeah, it will fit both the histogram model and also the Gaussian model. So as you can see, the progress is now done. Yeah, so it will tell you for the histogram model, each of the 10 bins that we asked for it to produce, the relative fraction for each. Okay, so it's finding somewhere in the middle of the range, which considering we did 0.5 to 3 and we wanted 1.8, that's looking pretty good. Okay, then it'll fit the, yeah, so the Gaussian model, which is usually quicker. And as I said, yeah, so the value it finds is 1.6 plus or minus 0.3. So consistent with this value of 1.8, but the reason it's not 1.8 is because I didn't simulate enough data sets. It would have been a very big file to download, but yeah, but consistent with it. Then probably good to show the outputs that we get. This one. So this shows the two distributions plotted. So the histogram model in black basically shows it's pretty good for this value of 1.8. It's pretty consistent with that. And then also the Gaussian model that you get with the equivalent one. But you could imagine a situation where your distribution is not shaped like a Gaussian, so where the histogram model would really be a very, very powerful way of doing it. Okay. Are there any other questions on that? I think it is time, but is there still a little bit of time for questions on any?
Yeah, we can go into the break a little bit and just maybe leave at least 5-minute break at the end. So 10 minutes if people have questions.
Great.
I have a question. How many would you have run, or is there a rule of thumb for how many you should run?
So how many sources?
Right.
So, I mean, yeah, I think it's a rule of thumb, but at the same time, the actual value that you do get out is pretty close, right? But yeah, maybe I think the issue was that I was trying to simulate variable photon index, but then I also tried to make the signal to noise variable. And then doing that, I ended up with a handful of points that were just extremely well fit because they were so bright, which I don't think that's a particularly realistic case. So yeah, it probably make it better if I simulated with slightly just fainter across the board, or just a certain exposure, for instance, in the simulations. So about the approximations for speed that Posterior Stacker does, Johannes, could you answer this just for the approximations?
Yeah, so it's using a hierarchical Bayesian model internally, but if, as Peter said, if you would do this all in one go, you would have to do the spectral fitting simultaneously with the population or the sample distribution fitting. And so instead it uses the posterior samples, but the important caveat here is, and that you should emphasize a lot, you have to analyze with a flat prior on that parameter. that's really important because you are trying to find the distribution across that parameter. And then what you have are posterior samples that describe your uncertainty. That can be upper limits, lower limits, or asymmetric, or as here, symmetric, doesn't matter. And basically what it's doing then is using those, in this case, 1000 posterior samples to do a numeric integral. So it basically takes these 1000 points and evaluates the sample distribution over those and integrates that. And so if those 1000 points are a reasonable approximation to this numeric integral, everything's fine. But if your posterior is very wide and all of them are very uncertain, then these number of samples might not sample well where your sample distribution will be. And then you will run into numerical issues. So it's definitely a good idea to vary this. So try, I don't know, you experiment first with a couple hundred, and then when you're happy with what you think is the right answer, you just crank it up by a factor of 10 and make sure that it gives you the same result, that it's numerically stable.
Thanks. Douglas, does that answer your question?
Yeah, I suppose the only other thing I'd wonder about is it, for example, if the population parameter you're trying to estimate is, say, horribly degenerate with something else, would that be a problem in that you're doing the two levels separately or not?
So from what I remember, I think Posterior Stacker can't figure out the degenerate problem, but I think if you were to solve this problem with Stan with a so I think, yeah, in that Baroncelli paper that I mentioned, they did this approximation with the Posterior Stacker method, and then also in Stan, where you're essentially analytically solving the shape of every posterior with a beta function, which is quite a flexible function, and simultaneously doing that and solving for the parent population to try and get around this problem that Johannes mentioned of having to fit the spectra simultaneously to the population. From what I understand, I think if you use Stan for those cases, I think it is able to overcome those degeneracies. But yeah.
Okay, good. Yeah, but I guess Stan is slower than this, so you lose out there.
A little bit, yeah. But, well, I guess it depends on the case, but yeah.
Yeah, easier problems are always quicker. So what can you do?
Yeah, true.
Okay, thanks.
Yeah, just comment on this easy problems. I have a general comment. So if somebody has an easy problem, you just have to use the standard methods. Don't go for the most complex analysis you can imagine. Just use the standard approaches. It all depends on the complexity of your data and your model, I guess.
I think so. If there are no other questions, then I guess we could call it a day. If anyone does have any questions or any problems that they experience with the exercises, please do let me know. I plan on leaving this website just leaving it, so it will be available in the future. So yeah, just if you run into any problems, just let me know or ask me or Johannes or yeah.
Hey.
Thanks.
Thanks again, Peter. To remind everyone else that we have Rafael Martinez Galarza is going to join us in about 7 or 8 minutes to do a Chandra source catalog tutorial. Thank you again for this tutorial, and I